Good morning, everyone. Thanks for inviting me here. I'll be talking about the Wurts Street Suspension Bridge Rehabilitation Project. I'm just going to start with a project overview. I'll be giving a little bit of the history of the bridge and our project history as well, both the design and the construction. And the project is currently under construction. We anticipate it being completed this year, so I'll have plenty of construction photos as well. So project overview, the project involves a comprehensive restoration of a 100-year-old suspension bridge. The bridge is owned by New York State DOT Region 8. Modjeski and Masters were the engineer of record. Construction inspection is being performed by GPI, and the contractor consists of a consortium of various folks under the Wurts Street Bridge Constructors umbrella: Servodone, GCCom, D'Annunzio, Northeast Structural Steel, Ahern Painting, and some other ancillary support, as well as construction engineering from those folks. So the bridge itself is a suspension bridge, three-span suspension bridge with a continuous stiffening truss, kind of small by suspension bridge standards, 705-foot main span, with total length of a little over 1,000 feet. Main cables are 10.5 inches in diameter, made by the John Roebling's company. And there's the main cables are anchored into rock on both sides, good geotechnical conditions at this location. The bridge itself, as you can see from the photo, carries 2 lanes of traffic. It's 27 feet between truss planes. There's outboard sidewalks, so it's a little over 37 feet out to out. The bridge is located in Kingston, New York, crosses over the Rondout Creek from Kingston to Port Ewan. Originally, this section of the Rondout was part of the Delaware and Hudson Canal, and that canal was owned by the Wurts brothers, hence the name of the bridge. The bridge is owned and maintained by New York State DOT, and it happens to be the only suspension bridge that's wholly owned by that agency. New York State has plenty of other suspension bridges, but they happen to be owned by different agencies than the state DOT. The bridge has an interesting history. As I said, it's over 100 years old. It was completed in 1922, replaced a ferry that was at that location. Some of the major milestones that's happened since then: 1973, there was a redecking contract. This was significant for us because they installed precast post-tension panels, and all those joints did contribute to some of the deterioration, as I'll show you in some photos. 79 was another milestone when the main route that the bridge carried, US 9W, was moved. There was a new bridge that was opened adjacent to it, just to the east, as shown here. And in 1980, the bridge was listed on the National Register. It has some really unique details for a suspension bridge. It was designed by Steinman and Robinson. They went on to build many famous structures that are still around today, including the St. John's Bridge in Oregon and the Mount Hope Bridge in Rhode Island. They're most famous perhaps for the Mackinac Bridge as well. It was constructed by Terry and Tench. They had experience constructing other suspension bridges in New York City, as well as the Bear Mountain Bridge over the Hudson River, which was done just after this one. It has a continuous variable depth stiffening truss, so it's really unique in the fact that there's no expansion joints except at the very end of the bridge, which is actually pretty unusual for any suspension bridge, let alone one this size. And the bridge also has additional cable strands in the backstay. So this photo shows the strands that wrap up and around the main cable at the top of the tower, and this was a way to improve the efficiency of the cable during the design. I've been involved in the project since 2006. We were brought on by New York State DOT, and one of the first things that we did was perform an inspection of the structure. That was in 2007, and then 2008 followed by a main cable investigation. That picture shows how the cable was opened up and wedged open to look inside, and we wanted to make sure, of course, that the fundamental aspects of the bridge were solid, and of course you have to remove the wrapping wire and things of that nature to be able to really look at that element, something that's beyond the typical biennial inspection. We also did some geotechnical investigations at that point because we knew we had some problems with the anchorage, so we took some rock cores, and then the project kind of went on hold for 10 years because of lack of funding. In 2017, funding was obtained, and so we re-kicked off the final design. again starting with a detailed inspection in 2017. As we were wrapping up our design process at the end of 2019, getting ready for a bidding in early 2020, naturally COVID hit, so that delayed things a bit. And of course, the bridge continued its cycle of deterioration. So due to some red flags that were identified in a biennial inspection, the bridge was actually closed in September 2020. But we knew that this project was going to be coming very quickly. So construction actually started in the fall of 2021. And I said, we anticipate things wrapping up at least substantially complete by the end of this year. There might be some punch list items that transfer over to the following. So back in 2007, we had anticipated it being about a $33 million project. That was based on those results back in 2007. 10 years later, there was an increase of roughly $10 million. Those 10 years were not particularly kind to the structure. There was quite a bit of additional deterioration. Those precast panels that I was mentioning happen to have joints right over at the midspan of the stringer, so this happens to be a shot of one of those. So those additional 10 years of leakage without any paint system, what was something that could be cleaned and painted was now full of holes and had to be replaced. So that, with some additional inflation and some additional features, we added decorative lighting, et cetera, raised it up to about $45 million. Final price is going to be maybe in the $50 million range. We had some additional repairs, steel repairs and things that are pretty common for a rehabilitation of this nature. So what did we find when we first started out? Back in 2007, the main cables were actually in excellent condition. I've looked at a lot of other suspension bridges, and this one had probably the best cables that I've seen. Very few stage 4 wires, hardly any corrosion inside there because they used petrolatum while they were spinning these cables. It's kind of an old-fashioned way of doing things, but it actually preserved the cable very well. Water was coming right in through the wrapping wire and through the paint, but it would just flow right out. The anchorage eye bars, however, were not so great. Those are just as important part of the suspension system. They hold up the main cables. And that red arrow is pointing to the eye bars, those gray elements that anchor the main cable strands back to the rock. Those eye bars had a lot of section loss. I'll show some more detailed photos, but it's not uncommon for these types of structures to have that type of deterioration. But that was obviously a large concern. We had up to 50% section loss of some of those eye bars. The suspender hardware was also severely deteriorated. It has a U-bolt connection with threads, so it was pretty vulnerable to corrosion. It was an area that accumulated debris and was not able to really be washed out. So the ropes themselves, though, were in excellent condition. Even though they were 100 years old, we tested them, and they had the same strength as a new rope. So in order to meet the goals of the project, which was to have a 50-year service life, we recommended a full rehabilitation. The rehabilitation scope is pretty comprehensive. We started out with those anchorages that I mentioned, addressing those eye bars. We had to replace tower anchor bolts because they were deteriorated. All suspenders are being replaced, 114 locations. All bottom cord gusset plates were replaced at 60 locations. The tower links, which connect the stiffening truss to the tower, were replaced. The bearing pedestals, the anchor bolts were completely gone. We also restored the bearings at those locations. Full cleaning and painting and installing decorative lighting, not only necklace lighting on the cable, but also uplighting on the towers above and below deck. And given the historical nature of the project, we wanted to perform an in-kind rehabilitation. As the gentleman before me was talking about, they really didn't want the bridge to look any different at the end of the day. So it was important, of course, to restore the structural capacity. The bridge was posted in this picture for 5 tons. It had dropped down to 3 tons at one point, and then, of course, the bridge was actually closed. So we wanted to raise that posting to 20 tons so that it would be safe for emergency vehicles. But it really isn't intended for heavy trucks. The bridge was originally designed for a 10-ton truck, and we have that redundant nature here. The main line 9W is actually on an adjacent structure. We also did some non-structural improvements that were necessary, improving inspection access so that folks can walk up that cable a little easier, complete repainting, the ADA compliant sidewalks. ADA needs to be addressed as part of every project, so we have some passing areas, widened portions of the sidewalk to allow that to happen, and improving the highway lighting as well as the decorative lighting. So I'm just going to talk about a few of the major structural elements that were part of this project that were fairly interesting. The anchorage rehabilitation was perhaps one of the most important ones. This was very obvious from the biennial inspections. The owner knew this was a problem because it was something that you could see, and obviously those eye-bars attracted attention. This is just a snapshot from the original plans. We didn't have many original plans. There was about a set of 10 drawings, fairly schematic in nature, not very detailed at all. But this just kind of gives you an overview of how the cable is attached to the eye-bars, and that eye-bar chain is attached down into the shaft that was carved out of the rock, and that's what holds the bridge up. So if you zoom in a little bit on these eye-bars, what happens is where the steel and the concrete interface, you get condensation forming because of the different temperatures of the concrete and the steel. So you have a lot more wetting and drying cycles of that steel right at the concrete interface. So if you zoom in on that, you can see that's like 50% section loss. But I want to draw your attention to that line right there. We've removed some of the concrete in order to be able to properly clean and paint this area. And all the portion of the eye-bar that was embedded in concrete was perfectly well preserved. So it was just those areas that were right at the surface of the concrete that was exposed to the wetting and the humidity that deteriorated. So we were able to address that. What we did was we strengthened it essentially with some rock anchors. We transferred load out of those eye-bars into rock anchors to compensate essentially for the section loss. We used rock anchors because they have a relatively low stiffness, so they can provide a constant offloading force that flexes with the live load and temperature changes of the structure. This just kind of shows an overview. That red line is where the losses were on those eye-bars, and we installed the rock anchors through the concrete back wall and into the surrounding rock. They had roughly, well, depending on the location, 18 to 42 feet of bond length. And they had to be staggered on either side of the existing eye-bar chain in order to clear the eye-bars themselves, as well as the deviation saddle that was embedded back in that concrete. So in order to transfer those loads from the staggered rock anchors to the eye-bars, we had to install those jacking beams shown in green. The jacking beams bear on the existing strand shoe, which is in blue on the right. And so as we installed some hydraulic jacks to bear on the jacking beams in turn bear on the on the shoes, and that offloads some of the load, partially offloading some of the load in those eye-bars. And the offloading was really just to compensate for the section loss. So we didn't completely offload them. We basically just wanted to restore the original safety factor of those eye-bars to compensate for the section loss. That's a photo of the eye-bars after the anchorage roof and chamber walls were removed and the paint was removed. The load transfer process was monitored the entire time using strain gauges so that we could make sure that we were getting the load transfer that we anticipated. This is just another picture that shows the whole anchorage opened up. This allowed the contractor to template these jacking beams. Installing those, it's kind of hard to tell from the picture, but installing those, it was a very tight clearance between the strands. So he was able to template those. He used LiDAR actually to arrange all these things. Geometry was extremely critical in order to install these. But a picture on the left shows the new jacking beams installed, and this picture on the right shows the hydraulic jacks there. That were just installed temporarily while we performed the offloading process. I don't have pictures of here of the strain gauges, but we did have strain gauges monitoring the process while we applied the loads. And this has all been done at all four anchorages and was completed successfully. The anchorage roof is going back on as we speak, and we will actually we've installed a dehumidification system in each of the anchorage chambers, so that'll prevent that process from happening again. Suspender replacement was another unique and complex operation for this project. We had to remove all of them. Luckily, the bridge was closed during construction, so we allowed the contractor to perform the suspender removal one at a time without having necessarily any temporary support. The stiffening truss was capable of spanning between existing suspenders without additional support, provided it's limited to construction live load. The existing suspender connection, this is kind of a close-up, shows some of those threaded U-bolts. This one really isn't even as bad as some of the other ones. We had severe section loss, generally at the kind of the seat area where water and debris would collect. But what we wanted to do in replacing this connection was make one that was not adjustable, because the threads are vulnerable to corrosion. We wanted to install a weldment that was a fixed connection, and that would be much more maintenance-free. But in order to do that, we needed to know what the existing hole pattern was. Again, no record plans really of that level of detail. So we had the contractor remove the suspender at a few locations, remove the existing steel so we could look at the hole pattern. Unfortunately, it wasn't very consistent, and so we had to just modify our detail to allow for some oversized holes, as well as drilling some additional holes to make sure everything was mounted in there. The picture on the right shows the new weldment with the suspenders attached, and that's what the weldment looks like now attached to the truss vertical. And that's the completed project, complete at the suspender. So the key to all this, especially when you don't have any adjustability, is accurately measuring the length of the suspenders. On most projects, there's good records of the bridge. You have original shop drawings. You simply fabricate the suspenders to the original length. We didn't have that here, plus they had adjustability, and each one of those U-bolts was set at a different location. So we had to measure it. We used a combination of LiDAR as well as steel tape, along with calculating the length of the weldment itself and the location of the cable, the suspender over the cable. This bridge has a fairly unique cable band detail. All the cable bands are actually the same on this bridge. Most suspension bridges, the suspender is vertical as it passes over the cable. This one you can see has a kink to it at that cable band ear, and it passes over the cable in a perpendicular orientation. So we just calculated that rather than trying to measure that. And again, that process of measuring and verifying worked very well. All the suspenders were installed without a hitch. So deck replacement was another key element. Those precast panels that were installed in the 70s were heavily deteriorated. All those joints were leaking quite badly. They were located not only over the floor beams, but at mid-span, so the floor system was suffering pretty badly. We wanted to use a cast-in-place deck in order to eliminate joints. We used a lightweight concrete in order to maintain the dead load of the structure, very important for suspension bridges. The lightweight concrete employed internal curing. In order to keep the deck fairly thin, we had to use chromium reinforcement to compensate for the lack of cover. And then we had to have a very detailed staging plan for how to install that new deck. The reason that in the 70s they used precast panels is by just replacing one panel at a time, one section of the deck at a time, you don't change the dead load of the structure. And so there really isn't a very detailed staging sequence. In order to do cast-in-place construction, you have to remove large portions of the deck, and that you have to have an engineered plan. There's significant stresses that are induced in the stiffening truss as you remove the dead load. In fact, the dead load is, stiffening trusses are designed to have zero stress under dead load, and they're only there to distribute live load. This is what the bridge looked like during the original construction. This is before actually the stiffening truss was completely riveted, but it gives you an idea of what the stiffening truss looks like before the full dead load of the deck is on there. It has that kind of curvature. We wanted to avoid that level of deflection, and so that's why we planned out our staging plan the way we did. We came up with something that involved 6 stages. Essentially, the idea was if the contractor followed this plan, he wouldn't have to do an additional analysis. We included a construction live load of 1,000 pounds per linear foot, plus a 20-ton concentrated load. But the contractor did have some better ways. He had his means and methods that he wanted to use, and so he did some analysis to alter the staging plan that we had shown. And he had some very good ideas. So he really wanted to get additional access to the stiffening truss for performing the repairs. So in order to do that, he removed the sidewalk and a portion of the deck around the stiffening truss. But again, that removed dead load. and he had to compensate for that. So he added a temporary barrier as a counterweight. So it was a very elegant solution, as a matter of fact. The areas in red were removed, the sidewalk and the outer portion of the deck, and then the temporary barrier was the counterweight, as well as providing protection during the construction phase. And you can see that allowed access to the stiffening truss and everything for a lot of the steel repairs that were performed. So by doing so, he was able to reduce the number of stages from 6 down to 4. He increased the size of the stages a little bit by utilizing counterweight. So again, you can do that, you can do additional removal of the deck, but now you have to compensate for that removal by providing counterweight, and he did that by using these water-filled drums. Again, an elegant solution because you can adjust the weight, you can adjust the location of where these were, and you can see they're all supported from the stringers, from the floor system. It also allowed him to remove the weight as we were placing concrete. So again, you want to maintain that dead load. So as the concrete was being placed, the water was drained out of the containers. And that's a current photo, obviously still under construction, but the deck came out very well. The tower link is another element that was of critical importance that ties your stiffening truss to your tower. And these were also heavily deteriorated. There's a lot of components here that I'm not going to necessarily go down through one by one, but suffice it to say, I'll draw your attention to the upper and lower pins. Those are what allow the structure to move, expand, and contract under temperature and live load. And those pins were heavily deteriorated to the point where they were no longer functioning. And so we replaced the tower link along with the gusset plate. All those members were heavily deteriorated. We developed a system to support support the stiffening truss while we were replacing those components, as well as provide a continuity splice while that gusset plate was being removed, so the bottom cord was continuous. And here's a photo of the new gusset plate on the left and the tower link on the right. These are pretty large components, so it's difficult to get a good photo of these things. And it was quite a challenge for them to erect this piece, but again, things went in successfully. All the gusset plates, as I mentioned, on the bottom cord were replaced. What happened is we have an outboard channel, and the water would just sit right on top of that channel, right against the gusset plate. So as you can see in the photo, very heavy deterioration right along that critical section. And as I mentioned, stiffening trusses of suspension bridges are kind of unique. They have essentially zero stress under full dead load. So you can actually do the gusset plate replacement without any temporary offloading as long as the full deck is in place. So this work was all performed when the original deck was there. Given the configuration of this truss, the floor beam is actually approximately mid-depth of the truss. So there's access to both the inboard and outboard gusset plates. The contractor performed the gusset plate removal one at a time, using the original gusset plate as a template for the new one, and was able to install those. Again, I don't want to minimize. It was tough work, but it all went together, and that's a final photo. Lots and lots of steel repairs. I won't go into all of them, but floor system, stringers, floor beam repairs, lateral members, cross beams, cross members for the outriggers holding up the sidewalk, a lot of new material. The stiffening truss was remained, but I would say the floor system and a lot of the wind system was new. And so that continued. And of course, on any of these types of structures, as you remove the sidewalk, you remove the deck, you see more steel repairs. Those all have been addressed. There was also some additional steel repairs on the tower area that are being worked on as well. Final two aspects of the project: improving inspection access. So you can see from this photo, there's no stanchion there. When we first tried to climb up this cable, you could move those hand ropes about 3 feet in either direction, so it didn't really provide you a lot of comfort. We're installing new stanchions, new hand lines, improved access from the cable itself up to the tower, so all these areas can be inspected properly in the future. And finally, the topping of it will be decorative lighting. This is a picture of the Mid-Hudson Bridge, not the actual structure. The lighting will probably be one of the last things that they install, but it's going to be color changing, They'll have programmable light shows, anything that you can pretty much imagine, and that's all remotely programmable. And so I expect it to be, it'll be pretty impressive to see. Incidentally, the dehumidification system that I mentioned is being installed in the anchorage will also be remotely monitored using a similar system so that they can make sure that the system's operational and the humidity levels are staying where we want them to prevent corrosion in the future. And I think I'm used up my time, and I'd be happy to take any questions that you might have. Thanks.
Hello.
Hi.
I recall you saying the cables were in good condition, the main cables.
Yes.
But how was the condition of the cable inside the anchorage? Was any PM done before the bridge was maintained? Was it maintained inside the anchorage?
It wasn't necessarily maintained. It was coated with grease, but it was protected inside the anchorage chamber, and they didn't have that same sort of humidity that was coating the eye bars against the concrete. So we did inspect those, and they were in good condition also. Yeah.
Even without the dehumidifiers, right?
Correct.
Yeah.
Yeah.
Perfect.
Hi, Blaise. Thank you for the presentation. Very informative. After the suspender cables were reinstalled, how was the equal distribution kind of guaranteed between the suspender cables with the continuous truss, given the adjustability was taken out with a fixed weldment?
So you're saying during the original construction, how did they do that?
Post the rehabilitation, to ensure that you had equal distribution across the suspender cables.
Okay. So yeah, basically these bridges are erected to geometry. You know, so the suspender, as long as you control the length of the suspender, then the loads essentially are going to be the same, right? So everything was hanging there originally. That's how they erected it. And then the stiffening truss is attached. So as long as we maintain that geometry, we would maintain the load. We did not actually verify the loads in the suspenders, and that's generally, you don't need to do that on these types of structures. The stiffening truss is somewhat flexible as well. So it has a way to distribute those loads. But yeah, it's really geometry control. By maintaining the geometry of the suspenders, you maintain the load. Yes, sir.
Blaise, thanks. Really interesting project. Since we're at a preservation conference, did you guys do anything, like any special features, or what did you do to try and make this last? Was there anything, because it's some of the places where water was sitting and collecting?
Yeah.
Did you guys do anything along those lines? Could you share that?
Yeah, I think several things. The deck in particular, using cast in place, fewer joints, makes it more maintenance free. We installed the curb, we improved drainage, again, getting that water away from the structure. Originally, there was a detail where the sidewalk was connected to the deck, and so that concrete was wrapped around all the diagonals and the vertical members of the truss. We actually separated the sidewalk from the deck. We left an opening, so that way, when water and debris gets in there, it can easily wash out and not get trapped. We mentioned the suspender connection is raised up above the truss, eliminated all the threaded components, and I think that's going to be much more maintenance free. It's all galvanized now, since that area was very hard to get in there and paint. The dehumidification system in the anchorages to prevent corrosion in that area. So it's still an old truss. It's still vulnerable, but we did as many things that we could to help reduce future maintenance needs. Okay. Thank you.